Hello, and welcome to my PIRL 2020 talk. I'm Dan Williams from Intel, and this is How This Experiment Ends, the Long Tail of Persistent Memory Enabling. I'm coming to you from my home office in Banks, Oregon, so if you hear any noises in the background, well, it's COVID times, and we're all used to it by now. So let's begin. If you recall from last year where we left off, we had just gotten through the gates, seen this sign in front of the fsync pillar of file system data integrity, and we had grabbed it and gotten electrocuted multiple times, but to deliver this facility. The map sync facility allows applications to use the optimized persistent memory programming model. It allows applications to flush from user space, not need to call fsync to do thousands of instructions just to do one instruction call to make something persistent. And this is success. The optimized persistent memory programming model is something you can do today in Linux. So we're done, right? Not quite. What else is there to do? Well, it turns out that on the path to that victory, that glorious victory, there was some litter left behind in this kind of form of features in the kernel that don't quite work with DAX, and so we skip out of those and don't enable them. If you notice, a lot of people do, when you use DAX today, you get this nice warning saying that it is experimental, which is frightening and scary. What it's really saying is that there are some features that need to be finished off, and it's not, at the time, it wasn't clear to file system developers that those could be done without changing semantics. I think they can be fixed without changing semantics, but let's go into a bit more detail about what are the features that are impacted by this current state of affairs. So I want to go over those features that affect those things, but also more detail about some of the other ongoing work and future work for persistent memory and what it implies for the industry. So that's today's agenda. The first one on there was Wrathlink, and I want to do a quick description of what is Wrathlink. Consider the scenario where we have two files on a file system. We want to copy the contents of A to B, and then we're going to write to file B. So that involves reading every single block of file A, writing every single block of file B, and then writing the part of B that we wanted to update. The problem with this is we waste a lot of time transferring the data and also storing duplicate data. Most of B is the exact same data as A, so why do we waste time transferring and storing all this duplicate data? So the same scenario with Wrathlink is, instead of reading all of A and copying it to B, we just do some metadata updates to have all the blocks of B point to their corresponding blocks in the same location as they are in file A. So we end up referencing them. We link them back, reflink. And then when we write to file B, we break the link, and B finally gets its own first real block. But we've saved all that time transferring, and we've saved all the capacity storing all this duplicate data. So what does this have to do with DAX? Well, let me go on to describe how Wrathlink works in the page cache. So in the page cache, even though we have one block shared between two files, we still end up with two distinct pages in the page cache. They just happen to be pointing back to the same physical block, but they have metadata representing where they came from. So the A0 page came from the first first block of file A, and the B0 page came from the first block of file B, even though they're sharing some physical space. So the page cache duplicates data, even though it's not duplicated on storage. This backlink pointer, or this pointer to file data, is called the page's address space. It's the file I know, the house that the page lived in, where it came from. Now, if you remember, DAX destroys the distinction. Well, it merges file storage, file system blocks, and page mappings. They become one and the same. So when you map a DAX page, you're actually directly mapping the DAX block. There's no chance for an indirection. We only have the file system blocks, which is exactly the same. Is the page. There's no place to store that. Where did this mapping come from? Information. But do we need that information? So the two attributes of a page that are used in the page cache are the mapping and the index. And like I said, the mapping is where the page came from, where it was mapped, and the index is this relative offset into that address space, into that file. But that's really only used mainly for page writeback. So we can have a generic page writeback facility that can just walk through a list of pages without needing to go look up any other information. Just look at the page and say, okay, you need to be written back to this location, and the page kind of is self-hosting that all it needs for page writeback. But DAX does not need page writeback, so we're good, right? The problem is DAX uses the mapping and the index for traditional, what I'm calling traditional memory error handling. So what is that? Let's consider this scenario. We have process A and process B. They both mapped file A down here on the DAX file system, but they've mapped this yellow block, and the yellow block is a poisoned page, where poison is a multi-bit ECC error. It's hardware detectable memory corruption that, when consumed by the CPU can detect it and flag it as an error. So in the first part of the scenario, process A has mapped the page, it tries to access it, and it consumes the poison, and the CPU takes a machine check exception. The machine check exception notifies a couple subsystems in the kernel. It notifies the PMEM driver itself, so the PMEM driver can say, whoops, we have a bad block here. Let me record that bad block. Let me record where that poison is located, so that people can look up where that is in the future, and go scrub it and correct it if they need to, and also go notify the memory failure handling code to say, okay, this process has done something, has consumed poison. We need to take care of it. So the first thing the memory failure code does is reverse maps it from the user address to a physical page, to a struct page, and then from the struct page it can say, go unmap that page, get it out of the process address space, and you see that the data we use to do that is the page mapping and the page index. And we walk through all the pages that were poisoned and unmap them. The next step after unmapping is telling the processes what happened. And if you've encountered the signal, the extra sig info handler data that comes with a machine check notification, you'll see these acronyms SRAR and SRAO. If you're wondering what those means, they mean signal recovery action required and signal recovery action optional. The process A gets an action required signal because it actually consumed poison. It actually has a data loss event that it needs to handle. Process B is notified that you haven't mapped, you haven't accessed it yet, so you don't need to take any action, but you have poison in your address space. Be careful. Most applications, they just get the SIG bus and stop and exit. But some applications actually take different actions based on SRAR versus SRAO. But you notice that at no time did anybody tell the file system what was going on. So the unmapping, the recording of bad blocks, it all happens behind the file system knowledge. So native file system memory error handling is a scenario where we tell the file system that the process can consume poison. And this is where a Wrathlink aware RMAP can be implemented in the file system. So we use the address to look up the physical location on the storage device for the file system. But then we ask the file system, tell us all the files that are impacted by this and who has those files mapped. And this gives the file system the opportunity to use its reverse lookup facilities to figure out which pages might be replinked that the file system knows about. It's worth pointing out that the XFS RMAP facility is fairly mature now. It was non-existent when this effort started. So it's something new that has grown up in the years since we initially did DAX. But now it seems capable of doing something like this. So we reverse map it, we unmap it without needing to use the page mapping and page index fields. And critically, we also record the bad blocks in the file system itself, so that a operation like file system tell me all the files that have errors can be done more efficiently. Today, you have to look at the physical list of bad blocks that the driver knows about and compare that to a physical list of extents for the files you might care about and match them up manually, and maybe those mappings change while you're looking at them. It's just not not the best user experience to kind of track those down. The SIG bus probably needs to stay there to get the application to terminate, but I expect once you can identify files that have access poison, I think it would be useful to have other facilities to notify the application this file had the problem versus this address, and clean some of that up. So that's the way to get. That's quite a bit of work to get rid of DAX's dependency on page mapping and page index. But we get a more comprehensive solution in the end. But you could say, hey, that's a lot of work. We're still doing all this work on DAX file systems. Do we just need to have a new ground-up native DAX PVM file system? And here are the caveats I see that need addressing. The first one is that of the proposed PVM file systems, the first thing they show is file system metadata workloads, file creation, directory, large directories, large number of files, kind of benchmarks. And XFS and ext4 DAX don't keep up. There are certainly scenarios where the performance properties of persistent memory, where it has lower performance versus DRAM, can impact applications. Even if they're using the optimized persistent memory programming model, they would have benefited from caching some things in DRAM. So sometimes DAX is not a automatic performance win. Page cache is better. And there are some workloads, especially large bulk transfer IO workloads, where NVMe is faster than PMEM. And that surprises people, but it also kind of makes sense because NVMe has an offload engine and PMEM does not. So what can we do to address these things? I think for the metadata problem, first needs to be pointed out that the DAX facility was not designed to accelerate metadata operations. So when these new file systems compare themselves to XFS ext4 DAX metadata operations, they're comparing it to something that those weren't designed to optimize. Nevertheless, these file systems are spending a lot of time generating block I/O transfers that could be just done directly to persistent memory if the file systems knew that they were DAX mappable. And there's some proof of concept patches out there showing that we could do this for XFS. I don't know about ext4, but certainly for XFS we have some proof of concept patches to accelerate metadata operations. And so maybe that claws back some of that performance difference versus these native DAX file systems. The page cache problem. So another feature I saw in the proposed DAX file system was marking executables as cacheable by default instead of using DAX for them. And today, with the new per file DAX setting, we can achieve the same thing. Just mark the entire bin directory, user bin directory, as DAX disabled, and you get the same effect. So I'm not sure how much more room there is for a new file system to automatically do this when we can maybe come up with policies for it using the per file DAX setting. As for NVMe faster than PMEM, there's certainly the DMA problem where PMEM needs to use the CPU to do data transfers. So we have new DMA engines like the Intel Data Streaming Accelerator that might help here, but just making the transfers asynchronous may also help as well, because XFS in particular is optimized for overlapping I/O, where it assumes it's going to submit I/O and go back and submit more and have a high queue depth. And the queue depth of PMEM is always 1, because by the time something is submitted, the work is completed, and that's not an assumption that XFS was designed with. So hopefully with offload engines, we see some of that performance come back. So do we need a new file system? No. Well, maybe not yet. And maybe prove me wrong with patches. I'm just not seeing it today. I think there's some of these mitigations that can be deployed, and we'll see what is left after those are deployed, and whether some of the advancements that these identified can be incorporated into existing Linux file systems. Prove me wrong. So meanwhile, all those kind of software things happening in the background, hardware is continuing to gain new features, and new features that have implications for persistent memory. And we're having to keep up with those. The first one is a feature we're calling stray write protection, and it's kind of an acknowledgement that bugs happen. And bugs happen in kernel code. And if a bug happens and it scribbles over some other part of memory, if it hits DRAM, it can be bad, but it's transient corruption. You could recover from it by rebooting. In most cases, a stray write to persistent memory is not transient. It's there forever. It can clobber things, and a reboot won't get it back for you. So as we're seeing persistent memory capacities go up into the terabytes, the vulnerability surface seems to be increasing to the point where PMEM could be impacted by a class of bugs that DRAM could not, just based on capacity. So we're looking at supervisor protection keys as a mechanism to solve that problem. And so a quick overview of what protection keys are. Take the hardware physical address space at the top, where PMEM is a part of that address space. The kernel direct maps the linear address space across all of memory, host memory, and PMEM is a part of that. And the plan is to mark the PMEM capacity as protected by a P key, a protection key. And the way that works is the page tables are updated to specify a specific key. And then when your code is running, it can apply the key it needs when it needs to access that memory. So we're running, in the blue areas, we're running normal ring 0 code, different subsystems. And then we call into the device driver, the PMEM driver, and for its access, it will bound its access with with the P key. It'll apply it and remove it. And the benefit of P keys is that turning on and off the protection of that memory space is done without needing to do any TLB flushes or page table updates. We could approximate the same facility just with page table updates, but P keys lets it happen without that overhead. So that would close off this potential stray write problem. Another area of hardware advancement is memory encryption, and we're looking at this multi-key total memory encryption facility as a more fine-grained way to protect persistent memory at rest. So we have a per namespace solution in progress, and we're looking at a per directory solution similar to what FSCrypt can do today in pathfinding. So some might say, hey, I thought persistent memory was already encrypted, and it is. It's protected with a passphrase per module. And so that looks like this. We have the CPU memory controller. It's sending out clear text to the modules themselves, but there's a cryptographic engine on each module that is encrypting it before it gets written out to media. So in this scenario, we have 3 different passphrases to unlock one big interleaved persistent memory region, assuming these three modules were all interleaved into one address space. So you need to unlock all 3 to get to that one large region. With MKTME, the encryption moves to the memory controller, and we have multiple of these keys. So what it allows for is, instead of encrypting at the module level where and unlocking entire regions, we can encrypt at the namespace level, which is more similar to DMCrypt or BitLocker or whatever flavor you like of volume encryption. And so it's a more fine-grained way to protect persistent memory at rest. But one of the feedbacks of customers that are evaluating persistent memory, they say, "Hey, this is just better. More capacity memory, maybe a lower performance, and I don't really care about the persistence. I care about the cheaper, larger capacity memory." So what impact is that having on Linux? It's kicked off this project that we've called memory tiering, and it is taking your PMEM device, your memory that's backing your PMEM device, and actually giving it back to the kernel as just another memory node on the system. Lower performance, but the idea is to have algorithms that take cold pages in DRAM and migrate them out to persistent memory, and take hot things in PMEM and migrate them into DRAM, so that you get the benefits of capacity, but without but also trying to time share the performance benefits of DRAM. But this one slide is effectively multiple years of work of trying to tune these algorithms to get it right and get it better. You may know something called NUMA balancing that has also been a work in progress. That's that is the baseline mechanism we're using to handle this migration. But keep your eyes on the memory development mailing list. This work is ongoing. So the path ahead, there's talked about a lot of things. We need to figure out a way to integrate DAX with some of these copy on write mechanisms. Wrathlink is one, but Btrfs would like to use some DAX facilities as well, and they need a copy on write solution as well. The new RMAP facilities in file systems allow us to do things we couldn't do when we first started this work, especially in the areas of error management and letting the file system give the user better information about where ECC errors have happened, where data has been lost, and how to manage it. As this stuff has been deployed, we've seen some performance corner cases that need some softening. We have some mitigation strategies for those. I think we need to let those pan out before we think about wholesale replacing entire file systems. The march of hardware goes on, and we continue to integrate with new CPU technologies, and we have it in, and PNAM has kind of launched this entirely new age of performance differentiated memory, whereas before maybe you only had to worry about NUMA, but now you have to worry about NUMA and other performance characteristics of your memory. So it's an interesting space to be in, a lot of work to do, and I look forward to answering your questions later this week. So thank you, and goodbye.